finite element method is terribly beautiful. There is a lot that goes into it. I think I counted like 5 or 6 different sections that we've done at this point that are kind of all rolling into this thing. It's very, very popular for a lot of applications. It is an integral technique as opposed to a differential technique. It's more akin to a finite volume than finite difference, for example. Like finite difference kind of concerns itself with a value at different nodes. You approximate the derivatives, and that's how you go about doing all that stuff. Has a lot of benefits. Kind of like finite volume, but more so. So it'll do complex geometries. We'll see a nice picture about that one. Irregular meshing, irregular material properties. We can look at, we can tweak the method according to the type of physics that we're doing. Not a lot of people do that, to be honest. It's kind of a very specialized thing. There's kind of like the general catch-all technique that we'll talk about. Not sure if we'll get to today. There are a few different ways that we can do mesh refinement. So the idea with mesh refinement is as it, well, exactly as it sounds, right? If we have a mesh that looks like, I've got to do triangles now. So FEM is all about triangles, right? If you have something that looks like that, and hey, you realize that something's going on here, we could subdivide this. So I've got a new triangle. Now I've got a new triangle. Now I've got a new triangle. Now we've got 2 new triangles, right? And there are different ways to kind of iterate onto that to better resolve those gradients or whatever feature of interest is happening there. There are 3 ways that FEM can do that. I'll try and get to that one. Very highly flexible boundary conditions. And the ability to solve boundary physics. So this one comes in through something called the weak form that ideally we will get to today. The idea is there are a few things that can happen to the boundary of your geometry, right? You could say temperature. You could fix the temperature at the boundary, that's Dirichlet. You could impose a heat flux, which is Neumann boundary conditions, or you could have something completely different happening on the boundary. So an example for this one, instead of temperature, let's talk about diffusion, right? You could fix the concentration, you could impose a mass flux. You could also say that along your boundary, whatever your species is, diffuses much faster, right? It's called surface adsorption and surface diffusion, and FEM can do that really nicely. No, Robin's boundary conditions are a mix of Neumann and Dirichlet. So if you have something where you say the heat flux is equal to 3 times the temperature, right? Then that's a Robin condition. Yeah, the boundary physics is actually a different type of physics that only lives on the boundary. So if you're concerned about the boundary element method, that's kind of where the tie-in for that one is. What's the other big one? Surface stresses, not to be confused with surface tension, are a big one, but what's the other one? Electrodynamics is really useful on the boundary because for alternating currents, all of your charges sit at the outer surface. So if you can just solve whatever your equations want to be at the outside, you don't need to mesh the inside of your mesh, which is massive computational savings. You've literally taken a 3-dimensional problem and made it into a 2D problem. It's really nice. All right, let's work through an illustrative example. Consider the ODE y prime is equal to negative y, right? We know that solution. We know it's a decaying exponential, okay? We want to approximate the function numerically between 0 and 1 with a line that's defined by boundary points, right? F at 0 is equal to a, but a is just 1. Don't even need to do that one. And f at 1, which is equal to b. So what we're going to do is we even know the solution to this. That was close. Touching it. Anyway, okay. So this is going to be our solution. We start off at 1, and b is the value over here. And what we want to do is find a line that gives us good explanation for that, right? Okay. This is our equation of the line. Hey, we're drawing lines. How do we find b? Anybody have some suggestions? I can wait. How do you find B in this situation? Glad somebody read the page, right? If you have f of x, you could just put it in here, right? You just take the derivative, you set it equal to the other sign, and you solve for it, right? When we do that, we get b is equal to 1/2. Good. And when we plot it, we get something that actually doesn't fit it very well, right? These are the direct methods where we're literally taking that value. It's called collocation techniques, actually. We're taking that value at the point and we're saying, okay, solve the ODE exactly at this point. Right? 0, 1, x. Okay? And the problem with that is that when we as our big monkey brains are looking at this, we're not looking for the solution at that point. We're looking for how well this is behaving over the entire domain. Okay? Gotta just scroll up there a little bit so nobody can cheat. How else would we do this? Let me pose it another way. We've done this, guys. We've done this like several times at this point. Why doesn't this look good? Somebody quantify that for me, please. Oh, okay. Who, by show of hands, thinks this stuff looks good? This is a good approximation of that. No? Okay. I've seen one. I've seen two people. Right? Why?
Find out what threshold. Very big problem. Insignificant.
Oh, it's not insignificant. This.
Okay, so we're assuming that it is significant.
Yes. Yes.
That is not.
Whereas it is not defined as good, it is not good. That better?
Yeah.
Right? Why is this better than that? No? No?
That's what I feel.
You got 2 points of intersection. There probably is some theorem that it eventually comes down to that, like intermediate function value, something, but that's not the root. Somebody else? Is the secant of the curve? Oh, well, that's the same thing, that it intersects, right? This.
I was gonna say that. Start and the end condition.
The start and the end condition are the same. Yeah, but it's not. But this doesn't satisfy the ODE at this point.
Because like.
You got it. Right? If we had the exact solution, instead of f as the approximate to this thing, if we actually had the real one, what would the residual be? Everywhere. 0, right? This is least squared regression, right? And for the cheaters in the back, least squared minimization of the residual, right? The whole point is, how do we have the least error over the entire domain? Right? So congratulations for just raising the bar there. Okay. Okay. Let's try and integrate this residual. Right? So the residual, everybody remember what the residual is in this context? Right? We bring everything to one side. For the exact solution, the residual is 0. All right. Okay. We can plug this in. We have f primed. That's b minus 1. We have f of x. That works out to this. You grind it all together. You have to be careful, and I did this at first, and then I thought better of it. You're not trying to minimize the residual, right? because the minimum of the residual is going to be something that looks like that, because this is a massive negative, and hey, we have now minimized the residual at negative infinity, right? We don't want to minimize the residual. What we want to minimize is the square of the residual, i.e. it's the least squares fit, right? Done this hundreds of times now. Maybe not hundreds, at least 3. Yeah. So we have an expression for the residual. We square it, we get this mess, and then we integrate, and we can do all this. We can do it all analytically. Here's the expression we get, right? What kind of forb? Why do I have forb here?
There's a curly.
Did I mess that somewhere? Yeah, here we go. There you go. All right. Right. So we integrate it. Now we have a, what kind of function is this? Quadratic, right? Second order in B. Okay. So the important thing here is through that integration, we've got an expression and integration. We've got an expression for the parameters. And the way that we find the least value is we minimize that expression. Okay. It's parabolic in B. The minimum is found that B is equal to 5/14, which means that's our function. Let's look at it. Much better. Great. You might still think that this actually like could be better. Maybe if you did it there. But if you take a look at the residual, we've got the good old underestimate, overestimate thing going on here, right? This is your midpoint. You've got part that's on top of it, part that's below it. The integral, which is the total area between those two, it's a signed quantity and it cancels out insofar as possible. Okay, so this works better because now we're doing the integral, right? And it works better. By working better, I mean over the entire domain, it looks better. Okay, we did something kind of funny though. We integrated r squared, and then we took the derivative of the integral, right? And it's kind of like, well, which are we trying to do? Okay. We could have actually moved that derivative inside. We could have said that the minimum di-f by di-parameter, in this case b, is equal to 0, is equal to di by di b, integral, right? Integrals and derivatives, you can swap the two, they're commutative. You bring the derivative inside, and now you get something that looks like this. Or generally, I think I changed this to b later on. So, sorry, I'm just gonna b. Okay. Does everybody see how I got here? Okay. This is called the method of, I keep messing it up, weighted residuals. Okay. And it kind of looks like you haven't minimized this quantity, but in fact you have. You don't need to throw the minimizer on top of this. It's already baked in. Yes. Thank you. Where would it be? Yeah, but then V swallows it up anyway. Okay. Let's try a different function for V. And we'll talk about why we're doing that a little bit later. So integrate the MWR method of weighted residuals, find the parameter. And now let's do a more convenient function of V, not W. That'd be hilarious. Fucking cat woke me up at like 5 o'clock this morning because he's like, oh, my food is empty. And meanwhile, he had just like licked all his food into like a corner of the thing. But the poor cat is 11 years old and he's got like 3 teeth left, so he can't even like scoop it. Anyway. Okay, so let's, without motivation, say that V is equal to X, right? Basically the simplest that we can possibly get. It happens to be the function that your weight is multiplied by, right? We said the function was 1 plus bx, right? That's that x that comes in, and we'll see why later. When we do that, we do the integral, we do our calculation, and now we don't need to take we don't find a parabola, we just find a linear system. B is equal to 2/5, which is very, very close, actually, to 5/14. So this is nice. But the benefit of this is that we're now doing something simpler. We're not doing residual squared. Now we're just doing residual times x. It gets even better. Okay. Problem is that we're still doing an analytical integration, right? And we don't want to be symbolic. We don't want to be analytical. We want to keep to the realm of numerics. So wouldn't it be great if we could express the integral as the sum of integrands evaluated at certain points? No. Squared residual is more accurate. Yeah. Squared residual is more accurate. This is something a little bit different. Yeah. Okay. Does anybody know a way of expressing the integral as a sum of the integrand evaluated at certain points? Gaussian quadrature. This was assignment 6, people. See who passed. Okay. Again with the W. This is what happens when I'm like copying notes out of one textbook for one section and then another textbook for another section, then everything gets muddled up. All right. Gaussian quadrature allows us to do exactly this. Now, Gaussian quadrature only applies between -1 and 1. And this integral is between 0 and 1. So what do we have to do? We have to scale our coordinates, right? For the integral, for the interval between -1 and 1, the Gauss points were -1 over square root 3 and 1 over root 3. Again, assignment 6. Okay. When we scale it, the scaling function is super simple in this case, and these are our new values. That's what we have to calculate. Evaluate the function, the integral, the integrand, right? The function inside the interval at those 2 points, and we get that, which gives us the exact same answer. Why is it the exact same answer? Will it always be the exact same answer? You already answered questions. Will it always be exactly? You think so? Anybody else? Will Gaussian quadrature always give us the exact integral? Seeing some trepidation. The answer is no. You already answered it in office session. The answer is no, it only integrates exactly up to a cubic function, right? Because that's the way that we calculated what the Gaussian points were, what the Gauss points were. We had to assume exact integration of a cubic in this interval, and so it only goes up to a cubic. But we can see that this is actually, less than a cubic in x. It's quadratic. Okay, great. So let's recap what we did. First of all, we parameterized the function in terms of the weighted sum of simpler functions, right? This is integration. Interpolation. This is interpolation with a linear basis. For this particular one, we said f was equal to 1 minus x plus bx, which is kind of a funny way to write this, right? This is one function. This is another function. This we just had to solve for, but anyway, because we had the Dirichlet condition, so we didn't have to bother. That's why a was there in the first place, right? And then we want to find the coefficient of the next one. So this is interpolation. Then we found a simple integral expression that minimizes the error of the approximation, i.e. the minimum weighted residual, least squares regression, right? Basically boils down to this. I'll show you the connection in a second. Then we perform the integration exactly using only the function evaluated, which led to a linear system. That's Gaussian quadrature. I'm not joking when I say this is like the culmination of almost everything that we've been working to at this point. And then we solved the linear system. And I did tell you at the beginning, every single thing that we're doing boils down to a linear system in the end. Here it is. Practical solutions for linear systems require sparsity. So how do we get sparsity into those matrices? Okay, this is for one value, and guess what? A dense matrix of value 1 is also, like, it's not technically sparse, but it may as well be. Okay. Let's go into the actual derivation. So let's say we have a linear, doesn't have to be linear. Thought I was joking about like actually going through and making corrections as I go. Here I am. So when we have a differential equation, we have some operator of u, of our solution, is equal to some function f, right? And we have boundary conditions too, right? This is over some domain, and then we have some kind of boundary conditions. So this nice script L is a differential operator. U is the unknown exact solution. F of x is some kind of function that depends only on space. I'm only writing this down. I didn't want to put vectors all over the place. So by x, I mean space. Just say that it's 1D, but it's actually ND. Doesn't matter. Okay. And then omega is the domain of the problem. So for 1D, omega is the interval, and the boundary is this partial omega. That's the notation that COMSOL follows. So that's one I learned. The boundary there are the points. So if that's omega, those are the boundaries, right? Later on, we're going to have areas, in which case our boundaries are now here, 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 right? Same thing for volume. We have the bulk, and then we have the boundary. That's the outside. That's our partial omega there. Yeah. We define now for the exact solution, this is exactly equal to f, right? That's the whole point of an exact solution. We can define the residual, which is a function of our solution. And for the exact one, it's equal to 0 everywhere. Because we don't have the exact solution, instead of solving for u, we're going to solve for UH. I don't actually know what the H stands for, but that's what everybody uses. And the residual in general will not equal to 0. Hence, we want to minimize this. Again, least squared regression. As we've spoken about multiple times now, we can always express a function as a weighted sum of our basis functions, right? This is a linear system, linear basis system, right? W are the weights / coefficients. Sometimes the terminology is. Phi I is called a shape function. In this context, it's a linear basis, but they call it a shape function. Okay. It's super trivial to see that, yes, this derivative is really trivial. Just comes straight through here. Yeah. We want to minimize this residual. Previously, we did the least squared regression. Now we're using this method, and there's a pretty good reason. That being that MWR is a weaker statement of the minimization instead of this minimal R squared. Show you what I mean. V is called a test function, and we have a few options. So this, as you pointed out, should be a 2. Right? If, oh, for Pete's sake, what is this thing? Okay. If we take the test function equal to 2 times the derivative of di r by di w, then we just get back to our normal least squared minimization. You guys see how that works? It's pretty easy. Good. Okay. If we say that the test function is the delta function, what that does is when you go to integrate something with a delta function, it's just going to only pop out those particular values. So if you have a set of xi's, right, when you go to integrate that with a delta function, it's just going to find R1 R2, right, which is x2, R3, blah, 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 blah. The integral is the sum, right? This is the definition and the methodology for the co-location methods, right? The first option that we did when we just found B using the residual at that point is this idea. Because we're only looking for the residual at the point where that weight mattered. Okay? The last one, which is the one that we're going to be using, is called the Galerkin method. Basically, what you do is you choose your test functions to be in the same basis as your solutions, which is convenient, but also has interesting properties. What that means is when you put this in, right, you can always take, you can move the sum outside of the integral, which is fine because integrals are distributive. So you can move the sum outside, and now you get something that looks like the integral of your residual times your shape functions, right? Where the residual depends on u, and u is defined in terms of those shape functions. This is what the NWE is actually saying. What it means is that the residual, this is an expression of orthogonality. If you think back to Fourier expansions, how you say that your sine of nx is orthogonal to cos of nx because the integral over that domain is equal to 0 unless your n's are the same. Right? You guys remember that? Yeah. This is the same idea. And what it's saying is that the residual can't be improved by moving that solution around that space. Kind of a weird way to look at it. And I don't actually have a better way to explain it. To be entirely honest, you're just going to have to take my word for it. It is related to the conjugate gradient method, where we also had our new search direction to be orthogonal to, or to be conjugate to all of the other search directions. This is the same idea. We found the residual that cannot be improved by moving in any of these other directions, where these directions are defined by your linear bases. That's why this is working. And it's also more in line with our ideas of the discrete numerical approach. What it also means is that we can choose our shape functions carefully and get sparsity into our matrices. Okay, we'll come to that one. I'm not sure if we're going to get to it today because it's time for calculus. 6 o'clock on a Monday evening, time for calculus. Woohoo! Okay. Any questions up to this point? About to take a left turn. It's a conjugate direction. No? Okay. I got it. Right? Okay. Our usual formulation of boundary value problems, and I'm saying boundary value problems and then immediately jumping into a time-dependent problem, because what we're going to do is a time marching scheme, so it just comes back to be a boundary value problem. Anyway, it's called the strong form. And why that is that it has certain assumptions about the solution, which seem kind of obvious, but as we see, aren't actually so obvious. For example, if the equation contains a second derivative, apparently the solution has to have a second derivative, right? Which seems kind of obvious, but that is the strong form of this equation. And we can see that there are weaker forms, where weaker means more flexible. Yeah? MWR leads to the weak form because we're introducing this test function, but we can also just introduce the test function and just manipulate things around, and we don't have a problem with it. What we have to do is we take our strong form, we multiply it through by this test function, and then we integrate the entire thing. And the magic happens with divergence of flux terms. And divergence of flux terms are prevalent, they're pervasive. Almost all branches of physics have some kind of divergence of flux because that's literally like stuff coming out minus stuff going in is the rate of change of stuff. Like it doesn't get simpler than that. Yeah. What you do. So as an example, consider the time-dependent heat balance, right? Here we're just using temperature is equal to U. Some people actually do that, I think, to avoid the confusion with time, right? If time is T, then calling temperature capital T is a bit weird. Okay, and we're going to use a backward Euler time marching scheme. So what we say is this, no surprises, substitute in the Euler expression and rearrange. No problems here, okay? We're solving for U at the current time based on the previous time. Okay. To get to the weak form, we multiply through by V everywhere, and then we integrate. Integral is distributive. Here I'm neglecting the whole like d omega, d partial omega crap. Like it's term by term. Otherwise, it just like there are so many omegas that it's confusing for everybody, especially me. Notice that we have this guy here. This is our divergence of flux. We multiply through by a test function. We can do funny stuff to this. We can do integration by parts. Do you guys remember what integration by parts is? Because I never do. If you need to remember what integration by parts is, and honestly, every time that I write this expression and do this transformation, I have to remind myself of this. duv is equal to duv plus u dv. Chain law, at least I can remember, right? You take one of these guys over here, and now you can say du v is equal to negative u tv plus d uv. Okay? This is essentially what we have here, but with divergence instead of u. Not the formal definition. This is my hand waving. Literally waving my hand on this one. Okay? V divergence J turns out to be, ignore the integral for a second, right? Gradient of V times the flux plus this integral of the divergence of V and J. All we've done is we did this, V times du in this case is that, right, is equal to J grad V. And then we rearrange stuff. Why this is important is that we have another way to write this term. We can use Green's theorem or divergence theorem to say that the integral of the rate of the divergence of something, of a vector quantity, is just the sum of everything around it. So this volume integral, this is why we're doing all these integrals, by the way, apart from the other benefits, but this is a nice feature to it. This integral over the volume turns out to be the integral of this quantity, test function times the flux, times the normal vector around the outside. Green's theorem, divergence theorem. Everything in here just turns out to be whatever is coming in and out through the boundary. Why this is so important. Oh, and sorry, and then J, we could just expand out and get lambda here. Okay. This is really cool because first and foremost, we've replaced a second derivative, which is the divergence of flux, with two first derivatives, right? Divergence of, or sorry, gradient of the test function times the gradient in your solution, which actually even has the same basis, right? That's a Galerkin method. What that means is that the solution no longer needs to have a second derivative. We can satisfy it in the weak sense by saying that we have this other function v, that when you take that gradient and multiply them together, we actually still get the answer, which is really cool because now for adjacent intervals, we can just use straight lines. Second derivative doesn't even exist, right? If you have a piecewise linear solution, right, that second derivative doesn't exist at this point. Not a problem. Still works. The next benefit is that now, right, there remember our two classes of boundary conditions. One is Dirichlet. The way that we handle Dirichlet for finite element is the exact same as we did for finite difference. We literally just take those nodes at the boundary and say, this value, fix it, right? The way that we calculated, the way that we implemented Neumann boundary conditions before was to have like the first couple of elements, the slope had to behave in a certain way. Finite volume had the advantage that we're actually explicitly putting in the boundary conditions, and this one has the same thing, which is nice because what that means is that the boundary flux only can be completely localized to the boundary of your system. It doesn't impinge on the inside at all, which is a more pure way to handle that. But it also opens the avenue. Sorry. Yeah. Come back to my big revelation here. The boundary conditions are now completely encapsulated in the weak form. If we want to put in any kind of normal flux, it goes in on equal footing as everything else in the formulation. There is no special treatment, with the exception of Dirichlet. Any kind of Neumann conditions, though, are completely integrated. We have not said anything about lambda. I think it was 2 assignments ago where I told you that lambda now depends on temperature, right? And that caused a big problem because now you're taking the derivative of that, and it's the chain line, you get nonlinear nonsense and all that fun stuff, right? We don't have to do that anymore because we didn't do anything with lambda here. We got it out of that derivative without changing it, which is really nice because now we don't need to bother with it until we do, actually, later on. But at least on the surface, it looks like we don't. This term is also where we can put in any kind of surface physics. Can go directly in there, which is kind of nice. It's kind of a more advanced topic, to be entirely honest, but that's a distinguishing feature of FEM. Okay. When we bring everything onto one side, this is the type of expression that we get now, right? We've just got this. This is our solution times the test function, blah, 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 blah. And then on the other side, we've got this, this source term, which turns out to be our previous time step. Okay, let's talk about discretization, and then I think that'll be that for today. You can see how this like goes on and on and on, eh? Like it's just, it really is. There's a reason why this is at the end of the course, because it's just like, then do this, then do this, then do this. Okay, discretization. Blah, 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 blah. And then we can finally actually talk about what these shape functions are, because we haven't actually defined that. Okay. Geometries can be complex. If you Google FEM, you're going to see stuff like airfoils, planes, wheels with funny hubcap designs. Any kind of additive manufacturing is all over finite element because it can conform itself and map out and discretize any kind of geometry. All you have to do is divide it up, tessellate it into these primary shapes. Right, tessellation being I was dropping my kid off at school, and there was an 8-year-old that was showing me a picture of her tessellating something. And I was like, tessellation, really? Like, okay, whatever. Right, all you're looking for is tiling. Tessellation is basically a fancy way of saying tiling. So you take these primary shapes and you fit them together to be space filling while still sharing nodes. So you don't have some funny business like here's one triangle, here's something like that. Right? This wouldn't be allowed because you have a vertex that's kind of in the middle of nowhere. I think they call it a hanging node. The nice thing about this is that we can do funny business. We can have a very refined mesh in here where lots of stuff is going on and then kind of expand our triangles out. You'll notice there aren't any hanging nodes anywhere, hanging vertices. And yet we can still have larger elements out here. Different material properties, not a problem. What we've done is we've partitioned the geometry into a finite set of elements. Finite element method. That's one of the interpretations of what finite element is referring to. There is another one that has to do with the shape functions. This meshing procedure is actually very, very complex, and there are people who have made entire careers based on it. There are software packages. The big one is Coreform Qubit, which used to be something else, and then it got renamed and renamed and renamed. It's out of Los Alamos. It costs money, but if anybody's doing like Bison calculations, for example, Bison, Marmot, any of those things, chances are they're probably going to want you to get a Qubit license so that you can generate these meshes. There is an open source version. It's called Gmesh, I guess Gmesh. And Flex, I don't know what FlexPD uses. It must have something under the hood. They all look very similar to that. Yeah. I have.
I'll take your answer.
I do know somebody who used FlexPD. No, other than like outside of McMaster, I do actually know somebody who did use FlexPD. Past tense. I am trying to not use FlexPD. Let me put it that way. Okay. The most flexible element is the simplex in whatever dimension. For 2D, that's a triangle. For 3D, that's a tetrahedron, right? Because that can conform and twist itself into whatever shape. Quadrilaterals are generally speaking superior in a lot of ways. And Andrew on Thursday might be able to talk about that, especially if you ask him about it. Depending on and then you can also do the 3D equivalents. You could do square-based pyramids. You could do triangular prisms. You could do rectangular prisms. You can do hexagonal grids. Hexagonal prisms are apparently very popular for CFD. They have a lot of nice properties there that you can tailor these things, but it doesn't change the underlying behavior of the finite element method. You can also mix and match. So I think Lucas, who isn't here, is going to be talking about his presentation on CFD and boundary layers, right? Boundary layers, and this is also to do with the assignment 7, right? If you have a no-slip condition here, you have where your velocity field is 0. Up here, your velocity is something in between. You generally have a pretty fast resolved gradient, hint, hint, right? Followed by some kind of tapering off. Turns out that CFD works really well on rectangular meshes. So what you just do is you put up a boundary layer that are squares, quadrilaterals, and then you just take over with triangles. And then you make the triangles very big, and you're out into the bulk again. No problem. Doesn't matter. Finite element is perfectly fine with it, which is nice. You do have to be wary of something called element quality. That's Consol's terms. Basically, what you're saying is that one of these edges doesn't go to 0, right? Even here, some of these guys, like here where you have these 3 guys, 4, 5, that are all connecting to a single point here, and this triangle is getting like super narrow, right? At some point, this is going to turn into a line, right? And once you're a line, then you have degeneracy in your element. So this is why like some of the more sophisticated meshing algorithms and stuff and tools have all this comprehensive stuff built into it. This is like a whole lot, right? I don't even know what step we're on now, like 8 or 9 of this stuff. The nice thing is that everything is algorithmic. So by the time that you guys got to FlexPDE, like it might have seemed like kind of oh, I'm just putting this and this. There's a lot of machinery that's happening under the hood and it's completely hidden for you, right? And it gets better. There's a lot more. We haven't even looked at the matrices yet. I don't think we'll even get there today. Okay. Notice how every single one of these elements is a translated and scaled version of a triangle. So what that means is that we can calculate our physics on one triangle and then just scale and twist it and piece it together for everything else. And that's exactly the point. Finally, we come down to the shape functions. Shape functions are designed to approximate the unknown function on each element. Typically, what that means is that whatever degrees of freedom are inside that element, I'll have to go into more of this on Wednesday because we don't have so much time. Whatever degrees of freedom are on that element, that shape function is 0 on all of your other elements. And this is where the sparsity comes in, because your shape functions are technically defined over the entire domain. So just show you guys. How long do I have? 2 minutes? Okay. Well, that's messy, but there's a better one. Da 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 da. Okay. Skipping to the end here. This is a linear, it's the most basic one. It's a first order Lagrange element. And basically what it is they call it the tent function or a triangular function. It's 1 wherever your vertex is on your mesh and 0 everywhere else. So this orange function here is defined everywhere in your domain. It just happens to be 0 out here, goes up to be 1, goes down, is 0 everywhere else. Over here, we have a different function, which is also a triangle, right? It's negative over here, but it's 0 everywhere else. Those zeros are going to cancel out. I'm giving you guys a Cole's Note version, and then we'll come back on Wednesday and do this a bit more rigorously. When we go through here, where's our weak form? Here. Remember that u and v are both being expanded in terms of our shape functions. Technically, this product has all of the shape functions multiplied together. You have phi 1 times phi 100,000 and everything in between. Every single one of those things are going to be 0, with the exception of the immediate neighbors. It's called small support. What that means is when you put it into the matrix form, you're going to get sparse matrices, which is nice, which is where the payday comes out. I'm going to call it there. That was a lot. Next time, so next class, we're going to talk about what these shape functions actually look like. Spoiler alert, they look like that. We're going to talk about how it actually works and then show you guys how to integrate it using quadrature and then actually do some practice problems and actually see how it works. And then on Thursday, my former colleague, Andrew Prudel, is going to be doing a virtual presentation and he's going to reteach this thing to you guys, followed by some applications. And why I asked him to do that is because this is like a whole bunch of junk all at once and hearing it from a different perspective. Andrew is much more of an engineer, I'm a bit more of a physicist engineer, hence engineering physics. So hearing that from him too, hopefully one of those two will click. It's a lot. This is a lot of stuff. Good. See you Wednesday. Okay. Do you guys all remember everything that we did in last class? The gist up until this point, a finite element, like it really does go on and on and on. We're almost at the end and then it explodes again. But I'll just show you guys like the introduction to the explosion. The whole point is that we're going to transform our PDE into, first of all, an integral equation. And integrals are generally better because then we don't need to worry about mismatched mesh shapes. We can do triangles of different sizes. We can do squares. We can do squares and triangles. Not a problem. Different material properties, all kinds of exotic physics. No problem. Integral is good. Next thing we want to do is we're going to interpolate our function, right? We're going to interpolate the unknown solution, which means break it down in terms of basis functions, right? Weighted basis functions. No problem. That's, where is that? Oh, it's coming up. Oh, it's coming up a long way away. Well, it's down here, but we'll get back to that one. Okay, so we're going to use our shape functions. We're going to approximate our unknown function using shape functions. Then we're going to solve the problem in a weak sense, where weak means instead of doing like linear regression of least squared regression, we're going to do this other minimum weighted residual formulation, which is all about projection. You don't really have to worry about that, to be entirely honest. Okay. What you're going to get is something called the weak form. And the weak form looks like this. You start off, this is time-dependent temperature. Your U is your temperature field, right? So change in time is negative divergence of flux, right? You do backward Euler time stepping. Right, so this is how we solve the PDEs, and now we get this nice expression here. Right, this is our current temperature. time step divergence of flux at the current time. And that has to be consistent with the time, the previous time. Okay. To get the weak form, if you're using something like Consol or ANSYS or Abacus, and I suspect Flex PDE, you don't need to know how to use the weak form. You don't need to convert it. If you're using something like Phoenix or FireDrake, you are going to have to use the weak form, but luckily there are a lot of examples, and to be honest, it's not that. What you do, you take your equation, you integrate over your volume, which is omega, and first of all, you multiply through by your test function, in this case b, and then you integrate over your volume. Integrals are distributive and associative, right? Which means that the integral of the whole equation you can just break up by according to term by term. This is working, right? Yeah. Okay. That's how you get this part. And then you do the magic. And the magic is very important because what you do is you take this integral of a function times divergence and you swap it. You take that gradient, you slap it on your test function. Test function is a low-level polynomial, super easy to calculate. And you get this, right? Which is your integral of a divergence of a vector field. Integral of divergence of vector field through Green's theorem, right? It means the integral of the divergence is equal to the surface integral around the boundary. So you transform it into this. Now you've got a volume integral and you've got your boundary integral. This term here, your flux times the normal vector, just turns into your boundary condition. This is just your normal flux, which means scalar. First of all, so you've gotten rid of another vector. And you've incorporated your boundary conditions directly into your equation. They are now one and the same, which is really nice. The funny thing is that you no longer, this equation does not require a second order derivative in order to solve. It doesn't even have to be defined, which means you could find a piecewise linear solution, right? You have, let's see if I have my marker. I do. Say this is my solution. If I had second derivative and I wanted to calculate the second derivative here, I would be SOL because it doesn't exist here. I have the first derivative on either side, but I don't have the second. Right? I don't need it. Weak form doesn't need it, which is nice. It doesn't actually technically need a continuous first order derivative, even, which is also very important. See? Okay. Weak form. We replaced the second order derivative with a product of two first derivatives. Great success. We don't need to have the second order time derivative. It doesn't even have to be defined, hence the weak form. We've incorporated the boundary fluxes. We haven't done anything with lambda. And we're going to see what happens when we do something with lambda. So lambda, this was assignment 6, where it 5 or 6, right? We made it dependent on the temperature and it just kind of messed everything up, right? We haven't done anything to it here. So we haven't done anything, but we have moved it outside of a gradient, which is also really nice because now we don't need to take complicated gradients or worry about Taylor. Yeah, and then there's this other nice feature that we have. We can put boundary physics in here too. Okay. Boundary conditions. This surface integral term is a boundary integral of the normal flux. Generally speaking, you're going to have one of 3 scenarios. You're going to know the normal flux. That's a boundary condition, right? You're solving heat transport, you know the radiative heat that's escaping, right? T to the 4th, sigma T to the 4th, right? That would be a heat flux, that would be a Neumann condition on your heat flux. The next one, if you do have that, all you have to do is plug it in. You just put that value in here and you do that integral, no problem. Or you ignore the term entirely, make it 0, in which case what you have essentially done is said that it's insulative, which is also very common, right? No flux loss. The next one is Dirichlet. right? Dirichlet is when you're saying the temperature here is this number. What you do in order to do that, you don't put anything into this term. You say it's 0, but you put that value into your vector of unknowns. So you end up not solving for that degree of freedom at all because you give it. In which case, the flux adapts accordingly. So you fix the temperature and your flux becomes your slope at that point, at that boundary, becomes whatever it needs to be in order to fix that temperature. If you do something like COMSOL, they're going to mention something called a weak constraint. A weak constraint is a Lagrange multiplier. Right? The benefit to doing it like that way, if you guys remember talking about the equality constraint optimizations, don't worry about that in this context. Lambda ends up being the reaction force by which that constraint is affected. In this context, that means that's your heat flux at the boundary. So it is the heat flux which is required in order to keep the temperature at that value. Why that's useful is because if you really wanted to know like super high accuracy what that heat flux should be at the boundary, and there are a lot of cases where you would want that, you use that as a Lagrange multiplier and then you can calculate it directly. And it's a very accurate answer. But generally you don't need to. Okay, discretization. We're finally in a position to actually do something about this. The first part, I think I showed you guys this one already, right? Yeah. Using triangles, you mesh, you get narrower at the beginning, larger at the outside, no problem. Every single cell is a triangle, and it's all literally just copies of the exact same reference triangle that's been transformed and scaled. Yeah? Small support for shape function. What that means is that on every element, we're going to define a few shape functions, which are the basis of your solution. Those shape functions are only going to be non-zero inside that element. So any terms that look like this, where we're integrating between phi I and phi j, or grad phi I and grad phi j, is going to be almost entirely zero for almost every combination of I and j, except when both I and j are inside the same shape. Which means, because ultimately everything boils down to a linear system, we're going to get sparse matrices. Right? We've come full circle here. Let's talk about making those matrices. What we have to do is we have to take our weak equation and we're going to pull it apart. So this term, right? We know that our solution is the weighted sum of shape functions. Yeah? If you consider this, recalling that this is the weighted sum, and we've also said our test function is a sum of the same bases. We don't need to weight it this time. You'll notice. And since integration is a linear operator, when we plug all that nonsense into this term, we get something that looks like that. This becomes a vector, right? The sum of yi times something else. This is matrix vector multiplication. That's what matrix vector is. So is you define your matrix M for mass, because generally it's the multiplier for the time step. You define your M matrix as the integral of these two shape functions. Similarly, terms where you have something like this with the two gradients, you boil that down and you define a different matrix. This one's called your stiffness matrix. And you multiply that through by a vector. This vector is a bit more complicated because I'm still allowing lambda to be a function of u. Show you what happens when it's not. It just simplifies it down. Right? So with these two formulae, we've calculated, we've got this term. We're given this one as a boundary condition, which means we only need one more. And this one, we actually have two ways that we can calculate this guy. Because we know u of t minus 1, that's our previous time step, that's a known function. We could just integrate directly. We could just calculate that. Gaussian quadrature, whatever you wanted, no problem. Or you bring and then you get the matrix vector product again. That means that this weak equation becomes this matrix equation. And if you don't recognize this as a matrix equation, right, summing over I, here it is in matrix vector form. And forgive my my lack of consistent vector notations here. So, weak equation, boil down those matrices. Now you've got a single matrix equation, which is good. And because all of your elements are copies, transformed versions of a reference, you only need to calculate what these guys are within that element. And then you pop it out all over the place. I'll show you guys what that means. Since you know that those are 0, M and K for any combination that's not inside that element are 0. Everywhere. Small support. Inside it, you're just copying and pasting a template. So you do it once, and then you pop it out all over the place. I think I literally just repeated myself there. Here's just a nice little summary table, at least I hope it's nice, about the identities that we're doing. This is how we define our mass matrix stiffness. This is F, according to this source. I put B here, and this is just your boundary term. I'm going to jump over to another slide for a second, which I don't think I put on Avenue. I'll put it on afterwards. Yeah, okay. So this is how you define your matrix equations. The last step before we can solve this thing is to talk about the shape functions themselves. And this is the rabbit hole. Because shape functions alone it's like own separate independent field of study. So let me just wrap that up for a second. We've got a matrix equation for a set of unknowns. We can nominally solve at this point, right? We have a vector function f of a vector of unknowns. We can root them. Okay? What I need to teach you first is what exactly these guys are. Because so far we've come like almost to the end of this and we still haven't actually talked about what our unknowns are. Okay. And I'm pretty sure Andrew's talk is going to start off with what those unknowns are and move forward. So either you'll click on my more abstract version or his more engineering approach, and hopefully it'll click. Okay. Finite elements. Expansive field. People go into this head deep into this thing. What you want to do is you want to find, say you have a, I'll show you the bad one. Say you have an interval that's in 1D, right? And what you want to do is you want to approximate some unknown function on 1D. There are a few ways we could do this. We could say you have a single point in the middle, and it is constant everywhere, right? You have now done that. That's called Lagrange order 1, or order 0. You can also do 1, 2, and now you define a line, right? So these turn into, where did I put this in? Yeah, all right. For a particular type of shape, it's going to define a few things. It's going to define what kind of function you're approximating: linear, quadratic, cubic, Fourier series, right? You could do spectral methods, orthogonal, Lagrange, Legendre bases, Gauss bases, all these. It goes on and on and on. It doesn't have to be polynomial. It could be a harmonic. It could be there are bubble elements, there are curl elements, on and on and on. You want to match that to the type of physics that you're doing. Curl elements are going to be good in electromagnetics, excuse me, right? Bubble elements have to do with that divergence term. So they're good for anything that's conserved, right? For elasticity, you have wave equations. Maybe you want to do a spectral method because that's a wave, right? The other thing that it defines, the element defines, is what degrees of freedom you need to specify that function. If you were doing a Fourier series inside here, right? Your degrees of freedom would be the coefficients of your sines or your coses. The ones that we're looking at are simpler, thank God. What they do is they're saying define your nodes, which are the positions in the element, right? Lagrange, which is a simple one, at least has the vertices of your mesh, which is good and easy to understand. And what the degrees of freedom are actually talking about. So Lagrange elements have at least nodes at either side with the exception of 0, and they're going to look at the function value at those nodes. These nodes, these shape functions, are sorry, let me just quickly, before I go into there. An alternative is something called, for example, the Hermite element, where instead of the value of the function at those nodes, what you want to calculate is the slope. So this degree of freedom is the slope there, that degree of freedom is the slope there, and you have to do something like that. And what that means is that the slope is the continuous parameter between your model, which means different things for your other physics. Come back to that one in a second. Okay, Lagrange elements is literally the Lagrange interpolation function that we talked about, what, in like week 2 or week 3, right? Now applied to the nodes at the vertices of the mesh. So here's here and here. And they have the property that, phi is only 1 at the nodes. It is 0 for all other nodes inside the element. And through small support, they are 0 everywhere else. So these shape functions are only 1 in a single place for a single node. They are, however, non-zero everywhere in between. This is the magic. This is the differentiator between finite difference and finite element. In finite element, you have your functions are still defined between your points. They're interpolated between those points and they're used that way. Finite difference doesn't actually look at that. It just looks at the values of it. So finite difference, I think, can actually be back calculated out of finite element for certain types of elements. This is a more general case. Okay. The order of the Lagrange elements determines the order of your polynomial and how many nodes you need. For a linear, right, Lagrange order 1, you need 2 points, 1, 2. For Lagrange order 2, you need quadratic. So what you're going to do is you're going to add another node, and therefore degree of freedom right in the middle of your element. Now you can fit a quadratic, right? Similarly for cubics, and so on and so forth. You can keep going. Let's take a look at what these guys look like. Can I zoom out of this thing? I don't think so. That's disappointing. Can I make this full screen? There's a way. Oh, no, not that. Ah, all right. Lagrange order 0. So my element here is between 0 and 1. Lagrange order 0 just has a single degree of freedom, and that's in the middle of the interval. Okay. Oops. 1 is lines. No big surprise. There's one shape function. It's 1 here, 0 at the other one by definition. Here's where it gets a bit more interesting. Note that every single function here is only 1 at its own node. 0, 0, 1, 0, 0, 1, 0, 0. It gets messier. Doesn't matter. 1, 0, 0, 0, 1, 0, 0, 0, right? Same thing for all of those. What that means is that it's very efficient to put in.
The meta logo.
The what?
The meta logo. The new
Meta. Oh yeah. I wouldn't be surprised if it is.
Yeah.
Right. You've seen like Lagrange polynomials are all like they're it's just right foot. Okay. Continuity. Lagrange shape functions are defined at least at the element, at the limits of the element. Which means if we have a mesh like this, right? This element, this degree of freedom here is shared between two intervals. So you can have one that goes like that. It's also this side of the previous element. Then you have another one that looks like that, right? So even though they're different elements and they are not technically connected, they're overlapping. What that means is that your solution, when you actually go and calculate U, it's going to be continuous because your basis functions are continuous. Your flux, your derivative in general will not be. Because you're going to have a situation where you have something like that. Flux does not have to be continuous, but the good news is that it doesn't have to be. Your derivative will not be continuous. Your flux is generally almost continuous. Not necessarily, unless you put that in. So if you were doing the cubic ones where you're specifying the derivatives on the boundary, those derivatives are going to overlap, and therefore you are continuous in your first derivative. Not necessarily in your zeroth derivative, in your actual function value, right? So by controlling those things, you're capturing different types of physics. It gets messy. I'm not going to lie, it gets messy. Okay. That being said, there's something a bit funny about zero. Anybody see something silly about zero? It doesn't go down to zero, but where is the node? Where in X? All the other ones, right? All the other ones have nodes at the limits. Here. Right? At least. Right? But Lagrange order zero doesn't. It only has something in the middle, which means that Lagrange order zero is something called a discontinuous Lagrange element. And it is not continuous. It does not describe a continuous function. Exactly. There are reasons why you would want that. Again, if anybody does incompressible fluid flow or elasticity, you have a pressure field, right? You don't need that pressure to have a first derivative that's continuous. So you can use this and it becomes a lot more stable and easy to solve. But all this is again, like preconditioners is its own separate field of study. I'll show you the periodic table of finite elements. Let you guys play around there. Okay. These guys define, these are called tent functions. I just want to hammer home that yes, you can indeed represent any function you want using finite elements, right? This is the tent function. If you notice, the spacing is not at all even. This code is pretty flexible, so you can actually just generate a new random set and it'll always match it. Because this is only one here at that value, it's actually very easy to calculate the weights. Anybody guess what the weights are? Right? Your approximation is the sum of all shape functions. And only one of those shape functions is non-zero at this point. So how would you calculate the weight? Sure. That's the Bessel function. That's your X grid. This is your tent function. The coefficients of your solution are literally the function evaluated at that point. Right? Because what you're trying to do is U is the sum of your weights times your shape functions. Almost every single thing goes to zero except for one. 3. Right? U at x3. Right? Super easy to calculate. And this is not only is it non-zero, but it's actually 1, right? By construction.
So it's kind of basically the same thing as the radial basis, the RBF stuff.
Very similar. Very, very similar, except that RBFs are generally non-zero at every other point in your system. Unless you do, there is something neighborhood method or something for RBFs that truncate that. But yes, yeah, exactly. Okie dokie. 2D and 3D, it generalizes simply, where this is defined as simply. It doesn't look so simple to me. If you look a bit closer, what we've done, so these are Lagrange order 2. No, sorry, this is Lagrange order 3 elements. So Lagrange order 1 is just the one on either side, on either vertex, right? Lagrange order 2 puts one in the middle. 3 means that you need all 4 of these guys to specify it. You also end up putting a guy in the middle. This is the very centric middle, by the way, until you look that it's not even. And then box zero. And now you've got a quadratic surface over, well, in this case, it would be a cubic surface over a triangle, right? And this is calculated once. All that integration is done once for the reference and then just transformed. Sorry. Exact same logic for a quadrilateral, better known as a square. Why it's called a quadrilateral. And I know why it's called a quadrilateral, but why it's called a quadrilateral. Could call it a square, right? Exact same thing. You just do the edges, propagate that in, no problem, right? 3D gets even more fun, but it's the same logic. You've got 4, you've got 4, you've got 4, 4, 4, 4, 4, 4, and you just, that's it.
Why isn't that actually the center?
It is in the barometric center.
Which is what?
It is equidistant from all of its vertices. So this guy is that far, and that far. Yeah,
So if
it doesn't look it because it's splayed, but it is the same distance from all 3 points.
So if it was an equilateral triangle in the center.
Yes. Wait, equilateral triangle.
So all everything is same.
That is an equilateral triangle.
Then that should be in the center.
It is.
Equal, okay.
That is the center.
Okay.
Right? Come up and measure it afterwards. Who's this? Is Stephanie in the room? I'm gonna use her. There you go. Right? So like this is almost the exact same, right? This is the height. So 11. Okay. Exactly the same. Yeah. Go. Real life. Come on, guys. Real life. Real life demos. Okay. As I said, this gets super rich. You can define curl elements for vector fields. If you're calculating vector fields, i.e. electromagnetics, divergence of vector fields, discontinuous elements, spectral elements. Spectral are kind of interesting. Yes, thank you. It gets super funky. This is a very simple, very limited version of the full table of elements, but you can look at all kinds of different things. I can't really read this notation, so don't bother asking me. There is a background session. Feel free to look into that, but this is written by like hardcore mathematicians. So this is all like orthogonal vector spaces of Hilbert matrices and somethings. ChatGPT, yes, it will be able to interpret it. I found it pretty shaky on this stuff. I wouldn't trust it, right? But if you see this element type, it's got these values here that are looking on either side. This is a curl element. So your degrees of freedom here are actually the slope parallel to the edge. And you've got a divergence here. Yeah.
That's the same.
Oh, yeah.
Oh,
Oh, yeah. Oh, yeah.
the joy.
This is, guys, this is why finite element is so powerful. Because we're almost at the end, and finally I'm telling you what the bloody shape functions are. Right? Everything else doesn't care what the shape functions are. It's just you're doing the weak form, you're finding the matrix equation, you're gonna throw a root finder. Surprise, surprise, everything's root finding at that, right? But the magic of the finite elements comes physics dependent, and there's a whole swath of these things. Some will converge, some will not. Some will take forever. If you look at something like this, like, holy cow, that's a lot of degrees of freedom for every single element. It better be worth it. There are some funky ones. Here we have curls all over the place, right? Fields perpendicular to the, or in parallel to the edge. Where are some other funny ones? Right? Here's a funny one. Check this out. You don't have any nodes on the outside at all, which means that you don't have a continuous element at all. Right? There's no first order like C0, C1, or C2. So what are you even doing here? This is a discrete one. This is a discontinuous one, right? Which is great for fluid dynamics, actually. This bloody one is triangular on a square surface. Like, I don't even know what AAF is, right? It just goes on and on and on. Don't say app.
No. Isn't that surface arbitrary in our heads? So then what's the good of having a triangular thing on a square surface if the square surface is kind of in our...
Say that again.
Okay.
One more time.
Sorry, so like, you know the triangle on the square surface?
Yeah.
Why not just have triangle on a triangle surface?
I have absolutely no idea, man. Ask Mr. App. Right?
It's how the shapes fit together.
Yes. Yeah. It's constructed in such a way that whatever function is described by these degrees of freedom is like uniquely described because it has to be.
Then what's... You know what? I'll just accept it as it is.
Oh, don't ask ChatGPT, man, if you really want. Good luck interpreting the result. Let me know if you wanna change your project title. Change my project title to what on earth are these other elements? Oh yeah. So all that to say is there's like a really rich like field of actually being able to represent these functions. Okay. Let's actually solve some of these things. So if it is finally, it only took us 2 days to actually get to a real example, huh? Okay, so we've got a matrix equation. We are going to solve the matrix equation for a vector of unknowns. If it's in 2D, you ravel? You unravel the matrix, right? So now everyone is a single vector of unknowns because now you can throw vanilla linear systems at it. Yeah, if the PDE is linear, you can represent it as a linear solver. It will be sparse because of the small compact support, which means sparse matrices. That's obviously what you want to do. It will not be banded. With the finite difference method, you saw those banded structures. You will not be able to count on them here. And that's because of the irregularity connectivity of the mesh vertices. Let's solve a 1D heat balance with lambda equals 1, 0 to 10, subject to a heat flux on the left side and a fixed temperature on the right side. Initial condition is temperature 0 everywhere. We can calculate our mass matrix, right? It equals this. When you do the Lagrange interpolation polynomials of order 1, these are your equations. You integrate it, you get a matrix that looks like this. Feel free to check my work. Don't bother, it's Wolfram. Right? Stiffness, you do that exercise again. Now you have lambda over h. Okay? Note that h does not need to be the same. So let's make it spicy. Let's have the step size changing from one element to another, right? To drive home this point. These blocks belong to each element. So what we're going to do, right? And yes, this is Gemini generated. I will warn you guys, this is Gemini generated, regenerated about 10 or 15 times with me manually tweaking it because it did not give the right answer. Flat out wrong. So by all means ask it, but don't actually expect to solve it like that. No. No. I don't have. Well, I'll show you the features. Yeah, no, there's some really easy things to look at, and actually that's a quiz coming up, so you jumped the gun on that one. Oh no, it's an exercise. I'll show you where something messed up. Half asleep, man. All right, I got 8 minutes here. Okay, you define the length, you define the number of elements, time step, your final time. X nodes, this is your mesh spacing. This is a complicated way of saying that I'm going to concentrate a bunch of mesh elements up front and then have bigger step and a bigger step. You can do them however you want. Finite element doesn't care. This is the stiffness matrix, right? This is literally the implementation of both the mass and the stiffness. Now we have to take that block 1 per element and slap it together into the overall matrix, the big M and K. So what you do is you take your nodes, right? Your node spacing determines your step size, which is an input into those matrices. And what you have to do, you take your matrix. This is kind of important here. You take your matrix that starts off blank, and you're gonna like add these blocks at every point. That's what this is doing. You're calculating that block, and then you're just adding it. You're not replacing it. You're just adding it. Integration is all additive because of its associativity. So you take that and you add on your mass matrix and your stiffness matrix. You move on to the next one and you overlap. Mass matrix, stiffness matrix, and you overlap again, right? This is why your matrix isn't, and this overlap means that you have the continuity in the solution. That's the nice part about this. But don't confuse it with a block diagonal matrix. It's not. It's a tridiagonal in this particular case. But more generally, it's this beautiful Shank type picture. Here, I'll just show you what the matrix looks like. Applying the boundary conditions. Here's where we put in where we're going to tweak our stiffness and our mass matrix to make the Dirichlet condition 0 at the far boundary on the right-hand side. It's pretty easy to see what it's doing. Yeah, you just have to make the final element 0 here. The Neumann boundary condition actually comes in when we're building the matrix because it's part of that B vector. What I mean by that is, quickly going back, all this stuff is on the right-hand side of your system, right? Your unknowns are over here. This is all on the right-hand side. So all of this gets smushed together, including the Neumann condition. And then I put it into a slider to see the results. This is the sparsity pattern of the, I think this is the mass matrix, right? It's sparse, good. Initial time. As you time step forward, sure enough, you get flux at the beginning. It's going to rise, rise, rise. It hits the back, but because of that Dirichlet condition, it is fixed. Over here, this, first of all, this looks right because it's fixed here on this side. If you did calculate the gradient here, especially right at the edge, you would have to get like really fine. Ethan, to answer your question about like whether or not I'm actually solving these to check, by construction, they're obvious, to be frank. It is 0 over here, but also because you have a heat flux, that means that your gradient is 1 and your final solution is just going to be from 10 to 0. Necessarily, that's your steady state. Note something here. We built K and M, which are the matrices, outside of the time step. We don't have to do this assembly stage every single time. That's only true for linear systems, unfortunately. You can usually take out part of that matrix building, but it gets a bit hard to do. To the point where it's not really worthwhile. Just let the software do its thing. This is where Patsy really excels, by the way, because these things are so common. It'll track things, and there's something else here too. If the PDE is nonlinear, I've got 3 minutes left. We have to use a root finder. Hooray! Right. In this case, we are looking for the unknown parameters U. Right. This vector of unknown. The shape functions don't change. The shape functions determine the sparsity of those matrices. So even though the elements in the matrix are going to change from one iteration, let alone time step, one iteration to another, the magnitudes are going to be changing, but the sparsity pattern won't be. So tools like Patsy, the linear solver, will give you the option to say whether or not your sparsity pattern is changing. And if it's not, then it has a more optimized way of constructing what these compressed storage algorithms are actually doing. Yeah. Since the modern software, you have to construct it either in the weak form or just in the strong form, not even in the weak form. Usually these systems will have symbolic logic built in. So at this point, you can expect it to be able to calculate the Jacobian by itself. So when we're doing the root finder, it'll calculate its own Jacobian and therefore it'll be more efficient. You don't need to worry about that. Let's repeat the above exercise for lambda is 1 plus u. What we get is this guy, and we raise the time. We have improved the thermal conductivity, and therefore you would expect the hotter it gets, the more conductive it is, and it would follow a term like this. It would follow a form like this. However, this is actually wrong. Do not trust AI. Anybody see what the problem is here? I'll give you a hint because we're running out of time. It's somewhere here. That's because it's higher thermal conductivity at higher temperature. Therefore, it's going to be flatter the higher you are.
Really?
Yeah.
Okay, so that part's right.
Yes,
Okay.
that part is correct. Yeah. If you look here, you will see Linnell solve, which is an LU solve. But this should be a root finder. We should not have an LU solve in here. So this is kind of the danger. Yeah.
How is it working? Or like nonlinear equations and it's like throwing the solver at it.
Let me come back to that one. Something's funny in the code. You have to prompt it again and push it to actually use a root finder. And sure enough, when you look down here, it's actually using root, right? This is kind of like, we would call this a sanity check, right? Like, are you doing an implicit method without a root finder? Because if you are, then you're doing it wrong, to be frank, right? But that's super easy to see. And when you actually go and you run it, you see something that looks very familiar. It actually looks indistinguishable. However, it is not correct. Why don't you change it? Oh yeah, there we go. Notice how that one was taking a whole lot longer. That's because it was actually doing the implicit time stepper scheme instead of what we were doing before. What it was actually doing is accidentally something called an IMAX method, which is implicit explicit. And what that does is it takes certain terms, does the time stepping implicitly, and combines them with other terms, which are time stepped explicitly. And the idea with that is that the stiff terms, that's like totally advanced topic. It's called IMAX methods. By all means, take a look at it. But the idea is to treat the numerically unstable terms, and we know what they look like, right? Specially, but everything else in your system gets treated nicely with an explicit RK45, right? And then you can get higher order accuracy, and you just target the implicit ones. But